Long ago, I was editor of the Bulletin of the American Math Society, and I became aware of the great shortage of articles that were both interesting and comprehensible at the same time, so that ordinary people, ordinary mathematicians, could actually read them and learn something and enjoy them. And when I was elected president of the AMS in 2002, I thought it's time to do something about that. And so this series came to be. The idea was to be like the Bourbaki Seminar. Those are wonderful talks on deep mathematical things, unfortunately with mostly incomprehensible write-ups and very formal write-ups. And I thought, okay, we can do something which is broader in the sense that it incorporates some applied mathematics and other fields too, and at the same time more comprehensible. But it was important to get write-ups. And the naysayers at the time thought this would be an insuperable challenge. It's now 23 sessions later, and I'm happy to say that of those 92 desired write-ups that the speakers have agreed to give, I think we've only lost 4 in that time. So I'm very pleased by that record. We've been doing this a long time. I've been doing it a long time. It started and has continued with the deep collaboration of the editors of the Bulletin of the AMS. Susan Friedlander was my original partner in this, and this will continue with Alejandro Adem, who just sat down just in time. And but the series is, well, honestly, I've had enough of doing this organization, so I'm happy to pass on the job. It seemed natural to do it within the Bulletin of the AMS structure, and so it will be managed by some editor of the Bulletin in the future, starting with Daniel Ehrman, who's sitting right there. So he'll be responsible for next year's event. This is my last. I'm very pleased with the outcome of these talks, and other people seem to like them too. So I hope to keep going to them for a long time. Anyway, today we have 4 great talks, I think. First one by Elena Fuchs from the UC Davis. You can read her title there just as well as I can read it to you, so I'll let you do that. But I emphasize that if you feel too isolated way back in that corner over there, there's lots of room in the front that you could come and move down to. So enjoy the talk and enjoy the session. Elena.
All right, well, thank you, David, for organizing this session for 23 years and for, yeah? And also for inviting me to speak here, and to all of you for coming. And I should say a special thank you to the people who actually did the work that I'm going to be talking about today, which are Kate Stang. I don't think I see most of them in the audience, but I see Kate Stang, so there she is, James Rickards, Summer Hogg, and Clyde Kurtzer. And you will see their names in this talk quite a bit. All right, so I'm going to be talking about Apollonian packings, the rise and fall of the local to global conjecture. So before I get to Apollonian packings, though, I want to go to an example that one usually sees like in an elementary number theory class in college. So let's look at integers that can be written as the sum of 3 integer squares. I'm doing this so that we can sort of get an idea of what local to global number theory is all about. So what we learned in undergraduate number theory is it can be useful with these kind of Diophantine equations to take a look at the equation modulo various primes and powers of primes. And then what you might discover if you do that is that this number n can never be congruent to 7 mod 8. And the reason for that is that squares, these x squared, y squared, and z squared, they all have to be either 0, 1, or 4 mod 8, and you just can't add up 3 of those to get 7 mod 8. But that's the only kind of place where there's a problem. There's no other quote-unquote local obstructions. By local, we mean, for example, at primes p or powers of primes p. Any integer can be written as a sum of 3 squares over the reals and over the p-adics as long as p is not 2. Okay. So in 1797, Legendre, with an asterisk, showed that actually this condition of n not being congruent to 7 mod 8 is sufficient to determine whether an odd number can be written as a sum of 3 squares or not. Any odd number that is not congruent to 7 mod 8 is a sum of 3 integer squares. And this is a local to global principle governing which odd numbers are of this form. So we just need to check a local condition, which is this n congruent to 7 mod 8, to determine the global answer, which is yes, you can write n as a sum of 3 squares. Now there's an asterisk there because actually Legendre's proof was incomplete. Gauss, I think, was the first to write a complete proof a few years later, and then Dirichlet, about half a century after that, came up with a proof which is much simpler and nicer. Okay. So that was over, looking for integer solutions. Now, it can be easier to just ask for rational solutions. And it turns out that is quite well understood for quadratic forms. The Hasse-Minkowski principle says that if a quadratic form with rational coefficients represents a number over Q, if and only if it represents it over the local fields, i.e. R and QP for every P. And the reason this is cool is that it's a lot easier to tell if something is represented over a complete field like R and QP than it is over something like Q. It's easy to find solutions there, kind of algorithmically. So that's over Q. X squared plus y squared plus z squared is special in that it actually is true that, well, even if you didn't know anything about sort of what kind of numbers can be written as sums of 3 squares, it turns out that if this n equals x squared plus y squared plus z squared can be solved over Q, you can take that solution and manipulate it in a geometric way into a solution over Z. So this was a result of a guy named Aubrey. This here is an excerpt of the published paper. It was written by hand. You can see over there he's looking at sums of 3 squares. He was not actually a research mathematician. I believe he was a school teacher, so he doesn't have a lot of published works, but this was a really cool result and method of his. But that certainly isn't true in general, that like if you can solve something over Q, then you can solve it over Z. If you want a slightly more general conditions for which it holds, you can take a look. There's a really nice section, appendix, I think, in Sarah's course in arithmetic about that. But we won't get into that here. Right, so like here's an example. 3x squared plus 13y squared equals 1. If you have an elementary schooler that really likes fractions, they can probably figure out that this is solvable over Q. You can take x equals 2/5 and y equals to 1/5. And so in particular, it is solvable over QP for all P and over R. But it's clearly not solvable over Z, because the smallest positive integer that can be written as 3x squared plus 13y squared is 3. So 1 is too small. And in general, solvability over Z is harder than over Q. And the kind of problem we're talking about today is of that kind. It's dealing with integers. And actually, even, I would say, harder than these sort of Diophantine equation situations. OK, so that is my little preamble about local to global, what that means in number theory. Now, Apollonian circle packings. So the reason they're called Apollonian circle packings is they're named after Apollonius of Perga. You see a little 3D headshot of him over there. In his now lost work, The Tangencies, a little while ago, was trying to construct, he was looking at the following problem. You have 3 circles or lines in some configuration. Can we construct a circle using ruler and compass that is tangent to all 3 of those? So that's what he was looking at, and I'll mention one of the things that we think he did come up with in a little bit. He did not, as far as we know, he did not actually draw any Apollonian circle packings. The first known mention of an object like an Apollonian circle packing is actually in a letter from Leibniz to de Bos in 1706. So it was a philosophical letter in Latin about like soul searching. I'm not a philosopher, so I won't go there. But what he wrote was imagine a circle and draw 3 other circles that are the same size and as large as possible, and in any new circle and in any new space between circles, do the same thing. Draw the largest 3 circles that are possible. And so he's inscribing these kind of tangent circles into these spaces, and imagine proceeding to infinity. Okay, so what this has to do with finding one's soul, didn't quite figure that out, but our construction is a little bit different. So here is a starting picture. We have 1 circle on the outside there and 2 circles on the inside. They're all pairwise tangent, and according to Apollonius, what he did realize is this: if you have 3 pairwise tangent circles, there are exactly 2 others that are tangent to all 3. So in this case, what are the 2 others? Well, there's one on one side of the 2 there and one on the other side. And so there's a unique way to inscribe a circle into those little spaces there. And you can keep doing this. So using the same principle of Apollonius, there will be a unique circle you can inscribe into each little space. So for example, like this little circle we just put in, it's the unique circle, unique other circle tangent to these 3 guys outside of the outside circle. Okay, so there's always kind of 2 options and 1 option for any given like little space like this. So you can continue this process indefinitely in a well-defined way to get a packing of infinitely many circles. Okay, so what does this have to do with number theory? Well, so let me give you a little timeline of the, as far as I know, of the of how number theory entered Apollonian packings, or vice versa. So the first person that made the following observation was Friedrich Soddy, he was a Nobel Prize laureate in chemistry in 1936. So he noted that if you start with 4 circles, so I know we started with 3 before, but let's look at, say, this circle, that circle, the outside one, and then the 3 one there. So 4 pairwise tangent circles, if they have integer curvature, by curvature I mean 1 over the radius. So like this one, the outside circle has radius 1, these 2 have radius 1/2, those 2 right there have radius 1/3, and so on. Then all of the circles that you inscribe after that will have integer curvature as well. So these are 2 examples of these kind of integer Apollonian circle packings. And the reason there's a little minus side on the outside one is essentially it kind of specifies that the orientation of the outside one is different from the others. It's like the inside of it is like the outside, kind of. But there's also another reason that we'll talk about later why you put a minus in there. Yeah, once you have this notion of integer Apollonian packings with these infinitely many integers, what number theorists can resist starting to ask all sorts of questions about like primes and what integers appear and so on in one such packing. Well, so then there were a lot of papers between 1936 and 2003 that were sort of geometrically flavored, geometry, ergodic theory. But the next one, I would say number theory, was one of papers of Graham, Ligarius, Mallows, Wilkes, and Yan. So they wrote a series of papers on Apollonian packings, and one of them was called Apollonian Packings Number Theory. So easy to remember. And in this paper, they really just paved the way for number theorists to study these things, the arithmetic of these things. They proved quite a few results, and equally importantly, they asked several really key questions about these things that they were unable to answer in their paper, many of which have now been answered. But one of them was, is there a, oops, I'm sorry. Clearly, I'm not so good at this. There we go. Yeah. One of them was, is there a local to global principle that kind of tells you what integers appear as curvatures in a given packing? And they showed some data which suggested that there are obstructions mod powers of 2 and 3, and probably no issues anywhere else. And in 2010, so this Apollonian packings is what I studied for my PhD thesis. And I wrote a paper with Catherine Sandon where we made this kind of local to global conjecture that was really starting to take shape already in Graham, Ligarius, Miles, Wilkes, and Yan's paper, precise. So what we conjectured is that if you have a primitive integral Apollonian circle packing, I've already told you what integral means. Now, primitive just means that the GCD of all of the curvatures in the packing is 1. So if it weren't 1, you could just divide out that number and kind of scale the packing up a bit. But yeah, so primitive, if you have a primitive integral Apollonian packing P, consider the set of residue classes mod 24 of curvatures in P. So we're going to call that R of P. Then we conjectured that there should be some number, x sub P, depending on the packing, where if you take any x greater than that x sub P, it's going to be a curvature in the packing as long as it's admissible mod 24. As long as whatever it is mod 24 is allowed in that packing. It lies in R of P. Okay, so like for example, you see here 3 is a possible residue mod 24 in this packing. And so what it's saying is, well, maybe once you take any number bigger than 1,000,000, that is 3 mod 24, it's going to be somewhere in that packing. It's a really strong statement, if you think about it. And yeah, we presented some data that I'll talk about later. And unless somebody was really secretly not believing this, I think everybody believed that this was true, but just really hard to prove. So between 2010 and 2023, there were various weaker results proven, as well as generalizations of these weaker results to other situations. So I proved together with Bergan that if you look at the integers that appear as curvatures in a given integer packing, it should be a positive fraction of all integers. Right, so like things that are 3 mod 24, even if you rule out a finite set as 1/24 of all the integers. So the local to global conjecture does imply that. And then Bergan and Kontorovich proved a sort of asymptotic local to global principle, which is that, well, if you look at all the numbers less than x, that you would expect to be in the packing according to their curvature mod 24, according to their residue mod 24, but are not in the packing, that number is very small. It's less than x to the 1 minus epsilon for some positive epsilon. Okay, so all these great theorems, but then in 2023, Hogg, Kurtzer, Rickards, and Singh showed that actually the conjecture is false. So for example, they discovered that in that second packing I showed you, the minus 11, 21, 24, 28 packing, you never get any integers that are of the form n squared or 3n squared. And so infinitely many admissible curvatures do not appear. For example, 16 is an admissible residue mod 24 in that packing, but there are infinitely many squares that are going to be 16 mod 24. So you're not going to just have like some finite set excluded. So in particular, this means that like for some packings, this epsilon is like a half. Okay. All right, so we're going to talk about how that came about. But before I do that, I should kind of give you a little bit of background on how to study these things. Oh no, before I do that, there's one more slide. So they did provide a modified local to global conjecture for Apollonian packings, which is basically the original one, but in addition, you are going to rule out this set Q of P, which is a set of integers that might be ruled out by the quadratic and sometimes quartic obstructions that is detailed in their main theorem that we will see later. Okay? So it's saying, okay, well, local to global conjecture, we still conjecture it holds as long as you don't consider these integers that are like n squared or 3n squared or whatever, whatever that set is for the particular kind of packing you're looking at. And we'll make that more precise a little later. So yeah, just a couple comments. There are still many packings for which the original local to global conjecture may hold. And I'll tell you kind of what kind of packings those are later. This is still a really hard conjecture to prove. So it isn't like somehow we've crushed this old conjecture, it doesn't exist, there's nothing to prove. There's still a lot of interesting stuff to be done here. Okay, So some preliminaries about how you study these things. So we've talked about this geometric way to construct these. And in the geometric construction, the big observation was that to any 3 given pairwise tangent circles, there are exactly 2 others tangent to all 3. So there's an algebraic way to kind of interpret this, which is you can actually use algebra to find, so if you're given the curvature of one of those 2 circles tangent to whatever 3 ones you're looking at, you can use algebra to find the other. So they're related algebraically. And where is that coming from? So it's coming from this theorem that usually is attributed to Descartes, which should probably be attributed to Descartes and Princess Elizabeth of Palatinate. So Descartes and Princess Elizabeth exchanged many letters back in the day. And a lot of them were of the format Descartes would send Princess Elizabeth some math problem, and she would try to do it. So he sent her a problem sort of related to this, and she tried to solve it, didn't quite get it, but sent him some ideas. He used those ideas to sort of write a proof. Nowadays, this would be a joint paper, but back then it was not. OK, so what does this say? It's saying that if you have A, B, C, and D, which are curvatures of 4 pairwise tangent circles. And by the way, from now on, I'm going to refer to 4 pairwise tangent circles or the curvatures of those as Descartes quadruples. We have that they satisfy this quadratic equation 2 times the sum of the squares minus the square of the sum is 0. And if you have a circle that's like on the outside, internally tangent to the other 3, then you have to take it with a negative curvature. Otherwise, this won't work out. OK, so say we have a quadruple, Descartes quadruple ABCD in a packing. And so geometrically, we know how to generate another Descartes quadruple, A prime BCD, right? We replace A by the other circle tangent to the circles of curvature B, C, and D, OK? Algebraically, what we know is that A and A prime are going to be the 2 solutions to this equation here. So what I'm doing there is I'm fixing B, C, and D in that Descartes equation up there, and I'm solving for the last coordinate. So I'm denoting that by x, and here it's going to be x squared minus 2 times b plus c plus d times x, plus this constant term, right? So I've fixed b, c, and d, so that's some constant term equals to 0. Now, we all know that for a monic quadratic polynomial, the sum of the roots is going to be minus the coefficient in front of x. So you get that a plus a prime is equal to 2b plus 2c plus 2d. Or in other words, a prime is minus a plus 2b plus 2c plus 2d. OK? So here's a nice kind of linear algebra way of seeing this. If you imagine you take a vector, A, B, C, D, sort of column vector, and you multiplied it on the left by this S1 matrix. Well, what that does is it exactly fixes B, C, and D and replaces A with minus A plus 2B plus 2C plus 2D with that other solution. These other matrices are doing the exact same thing, except it's playing that game with fixing 3 other coordinates. Not B, C, and D, but in this particular case, A, C, and D, and replacing B with 2A minus B plus 2C plus 2D, and so on. And really what these 4 matrices are enabling you to do is fill in, like if you have those 4 circles, A, B, C, and D, it allows you to fill in all the little spaces between the circles that you see there. And so with that in mind, if you were to take your Descartes quadruple ABCD, whichever one you're looking at in your packing P, and you look at the orbit of the group generated by these 4 matrices, which I'm going to call the Apollonian group A, acting on that vector, that orbit is going to be exactly all of the Descartes quadruples in the packing. You're going to be able to access every single circle in this way. I won't say too much about this group. What I will say is it's a subgroup of the orthogonal group fixing that Descartes quadratic form, Q. Okay, and these S1, S2, S3, S4, they're all involutions. Okay, so that's an algebraic way to interpret this geometric object. Well, we're talking about local to global principles. So what do these packings and packings in general look like locally? So say modulo prime p. What do they look like? So I'm going to keep focusing on these two packings throughout this talk, PB and PC, we're going to call them. And let's say mod 5. Well, turns out that both of them have 144 different Descartes quadruples. What are they? They are actually just all the non-trivial solutions to the Descartes equation mod 5. And in fact, this would be true for any primitive Apollonian circle packing you take. Furthermore, it is true for any modulo any prime greater than or equal to 5. And this is something that was already known to Graham, Ligarius, Malles, Wilkes, and Yen. But as I said, something happens mod 2 and 3. You don't have that same nice situation. And furthermore, things are different, mod 2 and 3 for different packings. Or mod powers of 2 and 3. So we have a local obstruction there. Now, the good news is that, and this is something I proved in my thesis, roughly speaking, once we know what a packing looks like mod 8 and mod 3, so 8, we just have to go up to 8, 16, 32, all that stuff becomes clear from that point forward. Mod 3, once you know it is mod 3, you can deduce what is mod 9, 27, and so on, higher powers of 3. So if you know what a packing looks like mod 24, you can deduce what it looks like mod any integer d, essentially by piecing together the information of what it looks like mod 24 and what the solutions to the Descartes equation are modulo powers of primes greater than or equal to 5. Okay, so the hope is there's no other issues outside of this obstruction mod 24. So, just in case you're interested, PB, that first packing, only has curvatures that are in those 8 congruence classes, mod 24, and PC only has curvatures that are in those 6 congruence classes, mod 24. And by the way, it's true that all primitive integer Apollonian packings always have either 8 or 6 residues mod 24. We'll see more details on that later. And so, together with Catherine Sandon, we looked at numerical evidence which seemed to support such a local to global principle for these two packings. And we figured, hey, this local obstruction is coming from the Apollonian group A, right? It is. So we expected that other packings would exhibit similar behavior as far as the local to global principle goes. We didn't think the local to global principle might fail for one packing and not for another at that point in time. Okay, so David told me that I should take a break in the middle, and it is middle. So I'm going to resume in 5 minutes, and we can all do jumping jacks during that time. All right, so David is robbing you of one of your minutes of breaks. May it be recorded. No. Okay, so coming back to what I was talking about, right? I said that we had this numerical evidence. So I'll start now by showing you the numerical evidence. So we generated some histograms, and the best way to explain these histograms is just to look at them. These are all for the packing PB, that first one. So what is this? So let me just say, like over here, for example, see that 500, and above it you have like roughly 3.5 times 10 to the 4th. What is that saying? So this particular histogram is for integers that are 2 mod 24 between 1 million and 10 to the 8th. That's what it says down there, if you can read it. So that data that I just told you tells us that there are between 1 million and 10 to the 8th, 3.5 times 10 to the 4th numbers that are 2 mod 24, which occur exactly 500 times as a curvature in the packing. Well, it's not quite that because this is a histogram. So that many that occur in some little bin around 500. So it's interesting to look at the distribution, and it's kind of ask yourself what the distribution is. But the relevant thing to the local to global problem is that there's no bar above 0. So there are no integers that are 2 mod 24 in this range, which do not occur at all in the packing. And same thing here, no bar above 0. For all of these things, 3 mod 24 between 1 million and 10 to the 8th. What does that say? I can't even see. Is that 18 mod 24 between 10 to the 6th and 10 to the 8th, and 23 mod 24. Is that 23? Yes. It's hard to read from here. And in fact, for the other, there's 8 total histograms, and the other ones were showing the same thing, that there's no bar over 0. So it looks like, from that perspective, the local to global conjecture seems to be supported. And also, if you go out further and further for like your range of m's, that whole kind of bar, the graph thing will shift over to the right as you go further out. So further away from 0. Okay, well for PC it was a little bit different. Because, so by the way, you see these little gaps in the histograms. That's nothing to be worried or intrigued about. It's just a way, a product of the way these histograms were generated. So here, for 2 of the residue classes, 13 and 21 mod 24, which are down here, you had a similar behavior as for PB. There was no bar over 0. Now, for all the other residue classes, I showed 2 of them there. So I don't know if one can actually see it here. Can't really see it, but if you go into the paper and you zoom in to the little area above 0, you will see there's a little tiny bar above 0 for all the other residue classes. So you're getting a few missed integers that are, say, 16 mod 24 there in that range, 4 times 10 to the 8th to 5 times 10 to the 8th, that are not occurring as curvatures in the packing. All right. So what did we think? Well, we assumed that the issue was that, OK, for the PC packing, the thing is the growth there is a bit faster than in PB. So you have to go out further to get the same amount of sample points for the PC packing than you do for PB. And our computer program just couldn't go out that far. Maybe we just didn't go out far enough, is what we thought. Seemed plausible, but it was actually wrong. And I just keep thinking to myself, why did we never check which numbers were being missed? Like, because if we did, we'd probably catch on. But we never did. We just looked at these histograms. So to understand where things really went wrong, we're going to pass from like this idea of looking at an orbit of a group to a slightly kind of finer and nicer representation of what's going on by looking at values of a certain binary quadratic form. So this was an idea of Sarnak. He wrote a letter to Ligarius in 2007 where he came up with this observation that if you have a circle here of curvature A and you just fix that circle and you look at all the circles tangent to it, so all these kind of dark gray circles, then the set of curvatures, like with multiplicity, that you get tangent to the circle CA is going to be the same as the set of integers represented by this thing here. So what this is there's a binary quadratic form here. The coefficients are b plus a plus b plus d minus c, and d plus a coming from this quadruple. And we're going to call that binary quadratic form f sub c sub a of xy. So every circle has some binary quadratic form like this you can assign to it, but with a shift by a. So you have this minus a over there at the end. And you're going to take x and y to be relatively prime as we're looking at the integers that are represented in this way. So this was a key observation that was used both in my paper with Bergan and in Bergan-Kontorovich. Ironically, it is also what's used to show that the local to global conjecture is false. Okay, so let's talk about the fall of the local to global conjecture. So actually, when Hogg, Kurtzer, Rickards, and Stang set out to, or when they embarked on this journey of proving that this local to global conjecture was false, I don't think they realized they had set out on this journey. So Rickards and Stang were organizing an RU at the University of Colorado Boulder, and they were looking at a question that is not, is the local to global conjecture true or not? It was, for which pairs of curvatures does there exist a packing containing both at once? Okay, so it was a cute question there. And they came up with a bunch of data, and one of the kind of plots they made was the following. So say you have A and B are two residues mod 24 that co-occur in some packing together. So what they plotted is they plotted a point xy whenever there was no packing, such that both 24x plus A and 24y plus B occurred in some packing together. So you would expect from the local to global conjecture that these points should peter out as x and y grow, because according to the local to global conjecture, for, once you go out far enough, any number that's A mod 24 and B mod 24 should be occurring in this packing where A and B are allowed to occur together, right? But what they saw is they found one graph in which the points persisted, and they followed a kind of quadratic pattern. So let's take a look at this plot. Here it is. These are these missing pairs of curvature that are 0 and 8 mod 24. So A and B there are 0 and 8. And you see there's no petering out happening here. It just keeps on going and going and going. And so at first they thought that there was some sort of mistake. There was a bug in the code. But pretty quickly they realized it was not a bug in the code. The code was fine. And these numbers that they're picking up for a very particular reason, and it's coming from some kind of quadratic obstruction. So let me talk about these quadratic and quartic obstructions. Actually, I'm going to talk more about the quadratic ones, just because I won't have time to also talk about the quartic ones, but the idea is the same for both. So the first thing that they did was they wrote down what possible sets mod 24 can you have in Apollonian circle packing. So I told you that there's always either 6 or 8 possible congruence classes. I think that was something that was known before, but nobody ever wrote it down. They certainly didn't write down what all the possible ones were. And so here are all the possible sets, and to each of these, they assigned a type. So a packing is of type xk if there are x residues in that set R of p, which is a set of residues. So x is always 6 or 8. It's that first number there. And k is going to be the smallest positive residue inside of R of p, which is co-prime to 24. So what I want to point out at this point is that in all the types that have 6 residues in them, there's actually only one residue that is co-prime to 24. There's not more than one. Here's just 1, 5, 13, and 17. The rest are not co-prime to 24. Whereas in the kind of type 8 packings, there's going to be exactly 2 residues that are co-prime to 24, and that will contribute to these quadratic and quartic obstructions. So here, like you have 7 and 19, and then you have 11 and 23 are the two. All right, so here's the theorem, the main theorem that they proved. So they refine the type xk further by including these chi2 and chi4s. Sometimes they omit the chi4 when it's irrelevant. So basically chi2 somehow governs all of the quadratic obstructions, and chi4 says something about the quartic obstructions. And it turns out, as we will talk about this, that these chi2 and chi4 are a constant over the whole packing. And so here we go. And by the way, in this table, you'll see that chi2 and chi4 is always plus or minus 1. Here is, let's see, where is the bug eye packing? It is this one right there. Sorry, not the B packing, the PB. The 8, 11, 1. There are no quadratic obstructions, no quartic obstructions, and local to global conjecture may still hold in all the residue classes. Okay? There's one other such type. It is up here, the very first one, 6, 1, 1, 1. No quadratic or quartic obstructions in the local to global conjecture may still hold. The PC packing is right over here, the 6, 13, minus 1. And you have that for 13 and 21 mod 24, the local to global conjecture may still hold, but not for those other residue classes. Okay, so hopefully you get the gist of what this table is saying. Right, so we're going to talk about where the quadratic obstructions come from. So before I do that, let me define for you the Kronecker symbol. So this is like a generalization of the Jacobi symbol. You have, for our purposes, we're really only going to consider positive integers. There is one situation where you might have to consider a negative one when you're on taking the curvature that's on the outside, but it's actually not going to matter in this case. You could just drop that minus if you want, in a sense. So the Kronecker symbol, m mod n, where n has this prime factorization, is defined as follows. It's the product from over all of these prime factors, and then this symbol m mod pi to the ei. What is m mod p? So it's 0 if p divides m. If p is odd and m is a quadratic residue mod p, then it's 1. And for p equals 2, it's 1 if m is congruent to plus or minus 1 mod 8. And otherwise, it's minus 1. Okay? So a really nice property of this Kronecker symbol is quadratic reciprocity, which is the following thing. If you want to know how this m mod n Kronecker symbol relates to n mod m, you have to multiply by a power of minus 1. So the minus 1 to the odd part of m minus 1 over 2 times odd part of n minus 1 over 2. So n prime and m prime, those are the odd primes of m and n, odd parts of m and n, respectively. Okay. So that's quadratic reciprocity. Now I just want to remind us of this idea of Sarnax, that we have this quadratic form assigned to every circle that governs somehow the curvatures of the circles tangent to that circle in this way. And the binary form you see there has discriminant minus 4a squared, always. Okay, so the first lemma that we need to mention in order to define this chi2 is that for a primitive binary form of discriminant minus 4a squared, like the one we just saw on the last slide, there's going to be a unique, primitively represented invertible residue f of x y mod a, so relatively prime to a, up to multiplication by a square. Okay, and we're going to denote any lift of this value to the integers, to positive integers, by rho of f. Okay, there's various options for this rho of f, but that's how it's defined. So given a circle C of curvature A and P, we're going to define, we're going to take rho to be this row of FC, where FC is that binary quadratic form corresponding to C. And this chi2 of C for that circle is going to be defined as the Kronecker symbol of rho mod A, if A is 0, 1 mod 4, Kronecker symbol minus rho mod A over 2 if A is congruent to 2 mod 4, and Kronecker symbol 2 rho mod A if A is congruent to 3 mod 4. Now, something to point out here is, yeah, rho has different, you could have chosen different values for rho, but the way that your different values might differ is either by multiplication by a square, which doesn't change the value of the Kronecker symbol, or by adding multiples of A, which also won't change the value of these Kronecker symbols. So this is a well-defined thing, no matter what you chose your rho of FC to be. And so that's what chi2 of one circle is, right? So in particular, it's going to be plus or minus 1. It won't be 0, because rho is defined to be relatively prime to A. OK, so then what Hogg, Kurtzer, Rickards, and Sting noted is that if you have two tangent circles, C1 and C2, of curvature A and B, where A and B are coprime, then chi2 has to match up on those two circles. OK? So why is this? Well, what does it mean for C1 and C2 to be tangent? It means that A plus B is represented by both F sub C1 and F sub C2. Why is that? Because the fact that C1, oops, oh no. The fact that C1 is tangent to C2 means that the curvature of C1, which is A, can be expressed as F sub C2 minus B. So A plus B is represented by F sub C2, and for the same argument, A plus B is also represented by F sub C1. So that means you could take rho of F sub C1 and rho of F sub C2 to be A plus B, because A plus B in particular is relatively prime to both A and B. So you have to consider the type 6K and the type 8K. I'll just show you, what the argument is for the type 6K here. In that case, if you look at it, all the curvatures are either 0 or 1 mod 4, and A and B can't both be even because they're coprime. So one of them has to be 1 mod 4. So if you look at quadratic reciprocity, well, the product of these two chi2s is the product of these two Kronecker symbols. Now, A plus B mod A is the same thing as B mod A, because B is congruent to A plus B mod A, and A plus B mod B is A mod B. Okay? So these are just, flipped Kronecker symbols. And quadratic reciprocity tells me it's going to be minus 1 to the, so odd part of one of them minus 1 over 2 times the odd part of the other one minus 1 over 2. But we know that one of them is actually odd and congruent to 1 mod 4. So it's going to be of the form 4r plus 1. So 4r plus 1 minus 1 over 2 is an even number. So this is minus 1 to an even number, you get 1. And that gives me that they have to be equal to each other since the values are plus or minus 1. All right, not only, though, do two circles that are tangent to each other and have coprime curvatures have the same value of chi2, it turns out that chi2 is constant over the whole packing. Why is that? Well, because it turns out, so this is a picture that Kate Stang generated. This particular one is for a circle of curvature 15 and a curvature 11 circle, which are already coprime. But even if they weren't coprime, what you do is you look at all the circles tangent to both of them, these gray ones. And those, and this is also something that was already known in Graham, Ligarius, Malus, Wilks, and Yan, are all numbers that can be represented in this way. There's this polynomial here, where so you have A and B are the curvatures of the two circles, and then C and D are going to be some two other circles tangent to both of them. And you can find a number that is coprime to both A and B represented by that polynomial. So what that means is there is going to be some circle among those gray ones that is coprime to both that one and that one. So like, for example, 86 here is coprime to both 15 and 11. And you can always do this. So here, like by the last lemma or theorem, that these two have the same values of chi2. Those two have the same values of chi2. So they all have the same value of chi2. And you can go from any circle to any circle by walking along some tangent circles. So you get chi2 is the same over the whole packing. So you have this kind of restriction on what this kind of thing that governs quadratic residues is over the whole packing. Okay, one final lemma before we can see exactly where these obstructions come in. So they also showed that if you have a circle of curvature A, you can always find a circle tangent to it that has curvature coprime not only to A, but also 6A. Okay? So let's see where these quadratic obstructions come from. We're going to combine what congruence classes mod 24 are allowed to occur together in one packing with the fact that chi2 is constant over the whole packing. So just a reminder, here is like what the packing types are. I'm going to look at the types with 6 curvatures in them, and the case where there's 8 curvature or 8 residues, sorry, is going to be similar. Again, in these 4 types, there's exactly 1 residue that's coprime to 24 in the whole set. Okay, so here's the idea. Let's say we have a packing of type 6K, and you take a circle of curvature something times n squared, u times n squared. So we're going to try to rule out some u's. So we know by the last lemma that C prime is going to be tangent to some circle C of curvature, which is coprime to 6 times that un squared. Now, but there's only one congruence class mod 24, coprime to 6, if you're in a packing of type 6K. Because, I mean, if you're coprime to 6, you're coprime to 24. So M has to be congruent to that K mod 24, this very same K that's up there. Okay, so now let's take a look at some Kronecker symbols. If you take a look at this un squared mod m there, the Kronecker symbol, that's the same as u mod m because we can take away that little square there. It doesn't change the Kronecker symbol. And that is the same thing as rho of fc mod m, the Kronecker symbol there, because so fc tells you what curvatures are tangent to the circle C, and one of them is the one that corresponds to C prime, which is un squared. And that's relatively prime to M, so it is a, so in particular, so it is a relatively prime represented thing by that quadratic form. And so you get that this U mod M Kronecker symbol is actually chi2 of C, and hence chi2 of P. Okay. Now remember, K in those packings, in those types, is 1, 5, 13, or 17. So let's take a look at K equals 1. So that means M is congruent to 1 mod 24, i.e. mod 8 and 3. So what does quadratic reciprocity tell us? Well, we're looking at, I'm going to be looking at this, what values of U I can have. And really the only problem here is because the restriction of M is just modulo these 8 and 3, the only problem might arise for kind of 2 and 3. So if you look at the Kronecker symbol of 2 mod M, what quadratic reciprocity tells you for this particular like M congruent to 1 mod 8 is that it's equal to M, the Kronecker symbol of M mod 2, which is just 1 since M is 1 mod 8. Similarly, you'll get that the Kronecker symbol of 3 mod M is 1 as well. And so that means that like U n squared mod M, which is the same thing as this U mod M, you know, if U is 2, then that is possible as long as your chi2 of P is 1. And same with U, if U is 3, 3 n squared will be possible if chi2 of P is 1. But if it's minus 1, then you can't possibly have things of the form 2n squared or 3n squared or 6n squared because the Kronecker symbol of 6 mod M is the product of those 2 Kronecker symbols. Okay, so already we see that in this type 6, 1, 1, you have you don't have any quadratic obstructions, but in the type 6, 1, minus 1, you will have these quadratic obstructions of no 2n squared, 3n squared, or 6n squared. Okay, so there it is. I highlighted that row in in the table. Okay, well, you can look at the other k equals 5, 13, and 17. So for k equals 5, you do the same thing. You look at the Kronecker symbol 2 mod m, 3 mod m, and 6 mod m. So here you get that 2 mod m and 6 mod m, you get -1, and there you get 1. So if chi2 of p is 1, then you can get things of the form 6n squared, but not 2n squared or 3n squared, and vice versa if chi2 of p is -1. For k equals 13, you have this combination of Kronecker symbols. So in other words, things that are 2n squared or 6n squared can happen if chi2 of p is -1, but not if chi2 of p is 1, and so on. And here it is for k equals 17. So you can draw these conclusions. And of course, if chi2 of p is -1, you can also not have any curvatures that are squares, because that would give you a Kronecker symbol of 1. Okay, so what I want to conclude with is that quadratic obstructions here are arising, and the quartic obstructions, are arising in harmony with these local obstructions, because if you take a look at and it's not surprising once you see the proof, if you take a look at the obstructions, all the quadratic obstructions have to do with like 2n squared, 3n squared, and 6n squared, right? The local obstructions are mod 2 and 3. And for the quartic ones also, all the numbers are of the form un to the 4th, where u is some product of powers of 2 and 3. Now, what I also want to say is that somehow the residues mod 24, which are present together in any one type of packing, are somehow forcing these quadratic obstructions. And if they were just a little bit different, then maybe we wouldn't have the quadratic obstructions. So I would love to understand exactly what about the Apollonian group, which is what's governing these local obstructions, forces this to happen. All right, well, thank you, and happy conjecture proving to you.